So in this video, I wanted to just work some more examples where you have to add vectors together. If you're not completely comfortable with adding vectors, then watching this video will help you for the signature assignment, which is basically you're just adding 4 vectors together in that signature assignment. So here's the first problem. Let's say we have a person walking, right, or running, either one. Let's say they start at the origin. So they start at like 0, 0 in our coordinate system. They walk north for 5 miles. Then they turn and walk east for 3 miles. And then finally, they walk 70 degrees I'm going to write it as south of west. So they turn at an angle of 70 degrees south of west. Oops, south of west. And they walk along that line for 2 miles. And the question is, what is their net displacement or total displacement? Sometimes we say net displacement. So basically, I want to find d net, right? Net displacement equals question mark, right? And it's a vector, so I want to find it. And in fact, I want to find it in component form, so the x and y components of d net, or written in terms of I hat and j hat. And I also want to find it in polar form as a magnitude and a direction. Okay, so first of all, to get an idea of what's going on here, right? Let's kind of sketch this out. So first thing they do is they start at 0, 0. So if I draw a coordinate system here, okay, so let's say this is 0, 0, right? And they walk north for 5 miles. So they're going in this direction. So this is like their first vector. Let me call that D1. So that's the first displacement, basically. Then they walk east for 3 miles. So that's in this direction. So this is like D2. And then they walk, so it's 70 degrees south of west. So the way to figure it out is if I start at the tip of D2, right, I want to go, so south of west means this angle right here, right? It'd be basically in the 3rd quadrant. So 70 degrees south of west means something like this. So that would be D3, where this angle right here would be 70 degrees, right, south of west. And then what is their total displacement? Well, the total displacement would be from the tail of the first vector, so from the tail of D1, meaning from the origin, to the tip of the last vector, right, to the final position that they end up in. So in this case, this would be the vector that I'm looking for. This is like d net. Okay, so basically I want to add D1 plus D2 plus D3 to get d net, right? That's how I'm going to find d net. D net is going to be vector D1 plus vector D2 plus vector D3. Okay, so in order to answer this question, I need to find the components of each of those displacement vectors of D1, D2, and D3 first. Then I can add the components together, right, to get d net. So how do I find the components? Well, I'm going to draw each one separately, right? So if I start with D1, So first of all, we know that the magnitude of D1, which I'll just write as D1, is 5 miles. Remember, I also could have written it like this, right? With those double vertical lines. So that means the magnitude of that vector, that's 5 miles. But it's easier just to write D1 by itself. So there's a couple of ways you guys could do this. You could say, well, this angle right here is 90 degrees. So I know in general that D1x has to equal D1 times cosine of the angle, and then D1y has to equal D1 times the sine of the angle. And you could just plug in and you will get the answer with the correct signs as well. So in this case, if I plug in D1 is 5, right, and then cosine of 90, but cosine of 90 is 0, so this is going to be 0, right, 0 miles. And then in the second one, if I plug in 5 and then sine of 90 is 1, so I'm going to get positive 5 miles. That's maybe the easiest way to do this. Or another way is you don't even need to actually plug in any angles. Because it's right along the axis, we can just look at this, right? It's going straight up. So we know its x component is 0. There's none of that vector is in the x direction. It's all in the y direction. The entire amount, the entire 5 miles is in the y direction, and it's positive because it's pointing upward. So I would have gotten the same thing. I would have found that d1x is 0, and in d1y, the y component is 5. And in writing it as a vector, right, using I hat and j hat notation, remember that means I write it as d1x I hat plus d1y j hat. So in this case, it'd be d1 is going to be 0 I hat plus 5 j hat. And then typically what I do is I put parentheses around it and then put the units, right, miles. So it's 0 I hat plus 5 j hat. Okay, what about D2? So let me go to the next page here. So D2 is, they're walking east, right? So it's in this direction. This is D2. And I know that the magnitude is 3 miles. So again, because this is right along one of the axes, you could easily figure this out. You could say, oh, d2x, well, it's all acting in the x direction, right? The entire magnitude, the 3 miles, is in the x direction, and it's positive. So this must be 3, right? 3 miles. And in d2y, well, how much of that vector is in the y direction? Remember, this is x, this is y. None of it, right? It's all in the x direction. There's none in the y, so this must be 0 miles. The other way that you could have done it is you could have said that angle is 0 degrees, right? If it's right on the x-axis, that means the angle theta is 0 degrees. So you could have said, okay, in general, I know d2x is going to be d2 times cosine of the angle, and then d2y is d2 times sine of the angle. So in this case, this would be 3 times cosine of 0. Well, cosine of 0 is 1. Right, so this is going to be 3 miles. And then 3 times sine of 0 is 0, so this is going to be 0 miles. And you'll get exactly the same thing, right? So we know that D2 is going to be 3 I hat plus 0 j hat miles. Okay, then I need to do D3. This one's a little more complicated. So remember, we're in the third quadrant, right? D3. So it's something like this. We know the magnitude. It was 2 miles. And I know this angle is 70 degrees. Okay. Again, there's a couple of ways you could do this, right? You could just use this angle. Remember, this is the reference angle because we want to find d3x. So if I project this onto the x-axis, it'll be this value right here, right, d3x. And if I project this onto the y, I want the y component. So this is d3y. So I could just use that reference angle. In fact, I could extract out this right triangle that contains the reference angle, and I could figure out these values just by using right triangle trigonometry. So if I extract this out, then this is going to be 70 degrees. The hypotenuse, right, is the magnitude. That's 2 miles. And I'm looking for d3x, d3y. So then relative to the 70 degrees, d3x is adjacent, right? This is adjacent, and this is hypotenuse. So what trig function relates adjacent and hypotenuse? That's cosine. So I know that cosine of 70 must be d3x divided by 2. But then if I solve for, I can multiply both sides by 2, right? By 2, by 2. So then d3x is going to be 2 times cosine of 70 degrees. However, because it's pointing to the left, I know it's got to be negative, right? So I have to look back at the original picture because the vector's in the third quadrant, d3x is pointing to the left, so I know it's negative. So this is actually going to be negative 2 times cosine of 70 degrees. So it's often easier to use just a reference angle because then you just have right triangles. It's like right triangle trigonometry. But then to get the correct SIGN, whether it's positive or negative, you have to look at the picture. That's important. You have to add that at the end. Okay? So in this case, d3x is going to be negative 0.68 miles. So this turns out to be negative 0.68 miles. And then to get the y, so how does this relate to the angle? Well, it's opposite, right? And this is hypotenuse. So what trig function relates opposite in hypotenuse? That's sine. So I know that sine of 70 degrees equals d3y over 2. And if you solve this for d3y, it's 2 times sine of 70. But again, since it's pointing downwards, that the y component is negative, right? So this is going to be negative. So I have to attach that sign later. So this is going to be negative, if you work this out, 1.88. Make sure your calculator is in degrees, right? Not radians for this part, because all of our angles are in degrees. Okay. Let me show you another way that you could have done this. Okay, I think this is probably the easiest way, just to use the reference angle and use the right triangle. Another way you could have done this is you could have found the actual angle from, so this is D3. So remember, this is 70 degrees. I could have found the actual angle from the positive x counterclockwise. So that would be 180, right? This would be 180 plus 70. What's that, 250? So this is 250 degrees. And then it turns out, right, if you want to find D3x, you simply use D3, which was 2 miles, D3 times cosine of the angle. And if you do cosine of the angle from the positive x, it'll automatically give you the correct SIGN, whether it's positive or negative. So you could do that. If you're comfortable with this and you understand how this works, you could do this. I think it's easier when you're first learning it just to use a reference angle, but you could do whatever way you feel more comfortable with. So in this case, it would be 2 times cosine of 250. And this one would be 2 times sine of 250. Notice I don't have to put positive or negative because it's going to give me that correctly. So if I plug this in, let me grab my calculator. If I plug in 2 times, I better get the same answer, right? So 2 times cosine of 250, I'm going to get negative 0.68. Right, it had to be that. This is miles. And if I do 2 times sine of 250, I'm going to get negative 1.88 miles. So again, it's up to you guys. However you want to do it is fine. So ultimately, we know that D3 is going to be negative 0.68 I hat minus 1.88 J hat, right, miles. Okay, now that I have D1, D2, and D3 in component form, right, in terms of the components, I can add them together to find D net, right, to find what I really want, which is D net. So remember, D net is simply going to be D1 plus D2 plus D3. So in this case, D net is going to be, well, remember D1 was 0 I hat plus 5 j hat. D2 was 3 I hat plus 0 j hat. And then D3 was negative 0.68 I hat minus 1.88 j hat. And if I add the x components together, which means adding the I hats together, right? The x components are the I hats, so I'll do it separate. So it's 0 plus 3 minus 0.68, right? Those are all the x components, the I hats. And if I add the j's together, right, the y components, I have 5 plus 0 minus 1.88 j hat. I'm going to get, this is 2.32 I hat plus 3.12 j hat miles. So that is my answer for the net displacement, the total displacement, in terms of components, right? Basically, it's saying that this is like d net x, and this is d net y, right? The d net x is 2.32. It's the x component of my net displacement, and the y component of my net displacement is 3.12. Okay, so we have our answer, but often we also want to write this in what's called polar form, right? We want to find the magnitude of that d net vector and the direction of that d net vector. So what I like to do is draw this out. See how both the x and y components are positive? That means we're in the first quadrant, right? So if we were to draw this out, this is like d net x, right? That's like 2.32 positive, so it's to the right. And this is like d net y. And that turns out to be 3.12. So that's positive, it's up. So that means my net displacement vector is in the first quadrant, right? It's got to be this vector. That's d net. Okay, so I want to find the magnitude, which means the length of that vector, and I want to find the direction, which means this angle theta. Or in this case, I'll use phi for my angle. So what I usually do is I extract out the right triangle that contains the reference angle, which is that phi. So this is phi. I know this length is 2.32. I know this length is 3.12. I'm looking for the magnitude of d net. So how do I find that? Well, it's a right triangle. I know two sides of a right triangle. I can use Pythagorean theorem, right? So d net, the magnitude must be the square root of 2.32 squared plus 3.12 squared. And if you work that out, it turns out to be 3.89 miles. So that's the magnitude of my vector. And then to get the direction, the phi, well, there's several ways I could do this, but I know the opposite and I know adjacent, so I could use tangent. So I could say tan of phi is opposite 3.12 over adjacent. But then I don't really want tan of phi, I want the angle, I want phi itself. So here's where we have to do the inverse, right? Remember, if I have like a function of x or phi or whatever it could be, let's say a function of x. If I apply the inverse function to that function, like I form a composite function, then I get back x. It like undoes the original function. So if I apply inverse tangent to both sides, the left side and to the right side, then the left side, inverse tan of phi is exactly this situation right here, I just get back phi, right? Often people don't even write that, but really that's what you're doing. You're taking the inverse tangent of both sides. The right-hand side, you have to approximate that with a calculator, and you're going to find it's like 53.4 degrees. Okay, and since we're in the first quadrant, that you don't have to say like, you could, if you want to make sure, you could say like north of east, and that will, for sure we know that the vector's in the first quadrant. But if you give an angle just by itself, it's always implied that you're measuring from the positive x counterclockwise. And since we're in the first quadrant, you could have just given that angle, and that would have been fine. But if you want to be really careful, just put north of east, then we know we're definitely in the first quadrant. So that's it. So basically, we have our answer in component form and in polar form, right? So like in component form, that was the I hat and j hat, right? So we know d net was 2.32 I hat plus 3.12 j hat miles. If I want it in polar form, that just means write it so it has a magnitude and a direction. Then that's what I just did, right? So that would be, you could say d net is equal to, what was it here? 3.89, right? That's the magnitude. 3.89 miles at 53.4 degrees north of east. So that would be in polar form, right? It has a magnitude and direction. Okay, here's another example where I'm going to add 3 force vectors together. So let's say we have this ring, and it's right in the center, right at the origin. And I have one force pulling on it in this direction. We'll call this F1. Let's say it has a magnitude of 100 newtons. And let's say this angle is 30 degrees. Okay. Then I have a second force, F2. Let's say it's in the second quadrant like this. So it's pulling on the ring like this. So this is F2. Let's say the magnitude is 150 newtons. So I drew a little bit longer, right? 150 newtons. And let's say this angle is 120 degrees. And let's say I have one more force, say F3. Let's say it's pulling straight down this. And let's say its magnitude is 50 newtons. Okay, and so this angle, if I go all the way from the positive x counterclockwise, that's going to be 270, right? 270 degrees. So what I want to figure out is the net force acting on that ring that's in the center, right? So this ring, all those 3 forces are acting on the ring, and I want to find the net force. In other words, I want to add those 3 forces together. So the question is, what is the net force? So F net, which is really equal to F1 plus F2 plus F3, right? I have to add them together. So what is the net force acting on the ring? And again, let's do this so that we answer the question in component form, like I hat, j hat form, and then also in polar form, where we give a magnitude and direction of that net force. Okay, so to do this, I need to find the components of each of those forces, right? Each of those vectors. So let me start with F1. I'll draw it down here. So here's F1. Remember the magnitude was 100 newtons, right? So the length of that vector is 100 newtons, and this angle is 30 degrees. So I want to find the x component, so project this onto the x. This is like F1x, and then project this onto the y, and the y component would be F1y. So again, I would extract out this right triangle that contains the reference angle, which in this case is the 30 degrees because we're just in the first quadrant. I know the hypotenuse is 100 newtons, right? That's the magnitude of the force is the hypotenuse. And I'm looking for F1x. I'm looking for F1y. Now, F1x is adjacent, right, to the angle, and I know the hypotenuse. What trig function relates adjacent to hypotenuse? Cosine. In fact, if you always use the reference angle, then the x component will always involve cosine. In fact, if you use the typical angle, the x component will always involve cosine. So in this case, I know that cosine of 30 degrees is going to be F1x divided by 100. And if I solve this for F1x, it'll be 100 times cosine of 30. And I know it's positive, right? It's pointing towards the right, so it's got to be positive. So if you work this out, it's going to be 86.6 newtons. Now for the y component, it's opposite, so I know that sine of 30 is going to be F1y divided by 100. So that means F1y is going to be 100 times sine of 30, and that turns out to be 50 newtons. Right? And again, it's positive because it's acting upward. So if I want, I can write F1 now in terms of components, right, in terms of I hat and j hat, as 86.6 I hat plus 50 j hat, right, and that's newtons. That's a j there. Okay, so that's one. Now I got to do the other two, right? So F2, actually let me go another page here. So let's see, we're in the second quadrant, right, for F2, so it looks something like this. So this is F2. I know the magnitude was 150 newtons. I was given this angle, 120 degrees. So I can find the x component. So this is like F2x, and then the y component. This is F2y. Okay, again, you guys have choices here. You could use the 120 degrees directly, right? And you could just say F2x is going to be F2, the magnitude of F2, times cosine of the angle, cosine of 120. And that'll give you the correct answer with the correct SIGN. So if you understand that, maybe that is the easiest way to do it. But so in this case, this would be what? This would be 150 times cosine of 120 degrees. So if I plug this into my calculator, I'm going to get negative 75. Newtons. Right? And it makes sense because it's going to the left, so it should be negative. And then F2y is F2 times sine of the angle. So there'll be 150 times sine of 120. And if I plug that in, I'm going to get 129.9 newtons. Positive, right? 129.9 newtons. So again, if you understand that, that's fine. You could do it that way. The other way that you could have done this is you could have found the reference angle here. And how would you find that? Well, I know all the way from here to here is 180. So if I do 180 minus 120, that means that this must be 60, right? This is 60 degrees. And then we could have just extracted the right triangle that contains that reference angle. So this is a 60 degrees. The hypotenuse is going to be the 150, right? That's the magnitude of the force. And then now this is F2y. This is F2x. And then using similar, right, we could say, well, so now using right triangle trigonometry, right, we could say F2x is adjacent. This is hypotenuse. That's involving cosine. So I know that cosine of 60 equals F2x over 150. So F2x is 150 times cosine of 60. But the thing you have to be careful with, if you use just a reference angle, then we have to get the correct SIGN by looking at the original picture. Since F2x is pointing to the left, this has to be negative, right? If I just type that in, it's going to be a positive value, so I have to put in the negative. So if I do it this way, I have to attach the correct SIGN. So it's up to you how you want to do this. So in this case, this would be negative 75, right? You're going to get the same answer as before. And then F2y is going to be sine, right? It's opposite. So sine of 60 is F2y over 150. So F2y is 150 times sine of 60. And then since it's pointing up, right, that component is up, then I know that this is positive. So I put the sign later, positive. And this will be positive 129.9. So either way, like in this case, we used the actual angle from the positive x counterclockwise, and it gave us the correct answer with the correct sign, right, SIGN. Or I could just use always the reference angle, then I just have right triangles, and then I have to attach the correct SIGN later. Okay, I'll have the correct magnitude, but I'll have to attach the correct SIGN. Up to you how you want to do it. There's arguments for both points being better. I think when you're first learning it, this is the easier way, but you have to remember to add the correct SIGN. Okay, so either way, right? Now that we have that, we know that F2 is equal to negative 75 I hat plus 129.9 J hat, right, newtons. Okay, I need to do F3. So F3 is acting straight downward. So it's like this. We know the magnitude is 50 newtons. So again, because it's right on an axis, it's acting straight along the negative y-axis, I can immediately say, oh, F3x must be 0, right? There's no component of that vector that's in the x direction. And in F3y, all of it's in the y direction, the entire 50, but it's negative. So it's negative 50 newtons, right, for F3y. If you wanted to use the most general idea where we use the angle from the positive x counterclockwise, then this is 270 degrees. And then you'd have to say F3x is F3 times cosine of that angle. And then F3y is F3 times sine of that angle. So this would be 50 times cosine of 270. And that will give you 0. And if you do 50 times sine of 270, you'll get negative 50. It'll actually come out negative, right? You don't have to do anything with the SIGN, because if you use the angle from the positive x counterclockwise, it'll automatically give you the correct sign. So either way, but in this case, because it's so easy, it's right around the x, we know that that's got to be true, right? The x component is 0, the y is negative 50. So you don't have to go through all of this, but it will work if you want it. If you want to be very consistent, you could do it that way if you wanted to. Okay, so that means F3, that vector, is going to be 0 I hat, right, minus 50 J hat. So minus 50 J hat, and this is newtons. Good, I'm almost there. So now I can actually add these vectors together. So I have remember F net is what I'm after, and that's simply going to be F1 plus F2 plus F3. So in this case, F1 was 86.6 I hat plus 50 J hat. F2 was negative 75 I hat plus 129.9 j hat, and in F3 was 0 I hat minus 50 j hat. So if I combine the x components together, right, which means the I hat, so I have 86.6 minus 75 plus 0, right, I hat, and then combine the j's, I have 50 plus 129.9 minus 50 j hat. I'm going to get 11.6 I hat plus, and then 129.9 j hat. Right, that's F net. So that's the answer in component form, and this is really in newtons is the measurement. So this is like, again, this is like F net x, right, the 11.6, and then my y component of the net force is 129.9. Okay, so that's the answer in component form. If I want it also in polar form, if I want a magnitude and direction, then again, I usually draw this out. This is nice, again, it's just in the first quadrant, right, because they're both positive. So this is like just a small x component, right? This is 11.6. That's F net x, and then F net y is 129.9. So F net is going to be something like this in the first quadrant. Right, that's the only, it has to be there if it has a positive x component of 11.6 and a positive y of 129.9. It's got to be in that first quadrant. So I want to find the magnitude, and I want to find the angle phi. So I extract out the right triangle that contains the reference angle, which in this case is just phi, because I'm in the first quadrant here. I know this length is 11.6. I know this is 129.9. So I want to find F net, that magnitude. How do I do that? Pythagorean theorem, right? Remember, the magnitude is always Pythagorean theorem. So F net is going to be the square root of 11.6 squared plus 129.9 squared. And that turns out to be 130.4 newtons. And then to find the angle, right, I need tangent, but I want to actually find the angle, so it's inverse tangent. So it'll be theta is inverse tangent of opposite over adjacent. And if you work that out, it turns out it's going to be 84.9 degrees. And again, if you want to be careful, you could write north of east, but you don't really need to do that for this one, because we're in the first quadrant, and that angle is the same angle as measured from the positive x counterclockwise. Right, so that would be the answer, 84.9 degrees north of east. Okay, so hopefully that will give you, a few more examples so that you can do that signature assignment, which really is just the same thing, except you're adding, in the signature assignment, you're going to be adding 4 displacement vectors together to get a net displacement. So it's the same sort of idea. Great, thanks.